We discuss about compact operator, one of the important topics. Now discuss compact operator. First we start about from definition. Let xy be normed spaces and tx to y be an operator and tx to y be an operator. Then t is said to be compact if tc conjugate is compact, or tc closure, here closure is compact for every bounded set C, for every bounded set C in X. Okay, for every bounded set C in X. Now we also going to another observation about that. Okay, so first, every compact set is closed and bounded. First, every compact set is closed and bounded. Number 2, if tx to y be compact, then tc closure is compact for every bounded set C in X. Is compact for every bounded set C in X. Then TC subset of TC closure, and TC closure is bounded for every bounded set C in X, for every bounded set C in X. Then this implies that T be a bounded operator. Okay, now we also discuss number 3. If t x to y be linear, then continuous of t implies boundedness of t. Continuous of t implies boundedness of t. Implies boundedness of t. Again is our portion. If tx to y be a linear compact operator, then t is continuous, compact operator. Compact operator. Now, a continuous compact operator is called completely continuous operator. A continuous compact operator, continuous compact operator is called completely continuous operator. Completely continuous operator. Now we also discuss one proposition. Okay, we write the statement of this proposition now. Proposition: let xy be norm spaces. Let x and y be norm spaces, and tx to y and tx to y be a linear operator if for each sequence xn, if for each sequence xn in bx where bx is where bx is x belongs to x, norm of x equal to 1 equal to p10, then txn has a convergent subsequence, has a convergent subsequence. Now we discuss here. We also write proof here. Here bx equal to x belongs to x such that norm of x less than equal to 1 equal to p10. This one closed wall p10. Suppose that for each xn in bx, for each xn in bx, t of xn has a convergent subsequence, has a convergent subsequence. Then we have to prove that then we have to prove that T is compact. That is if xn be bounded in x then Txn has a convergent subsequence. Has a convergent subsequence. Now we erase our portion. Let Xn be a bounded sequence in X. Let Xn be a bounded sequence in X. Then there exists a constant m greater than 0 such that norm of Xn less than equal to m for all n belongs to n. Then 1 by m Xn is a sequence in Vx. Okay, then hence hence by assumption T of 1 by m Xn has a convergent subsequence T of 1 by m Xn. Thus Txn has a convergent subsequence Txnk. Okay, so we also discuss that xy be normed space and T be a linear operator if each Cauchy sequence xn in Bx, then Vx equal to x belongs to x norm of x equal to 1, that means p1 0. Then T of xn has a convergent subsequence. We also see here xn bounded in x 1 by m xn is a sequence in Vx, and then by assumption T of 1 by m xn has a convergent subsequence T of 1 by m xn k. Thus T of xn has a convergent subsequence T xn k. Okay, next here we write definition of relative compact. Okay, we write here relative compact. Let C be a subset of a topological space X let C be a subset of a topological space X, then C is called relatively component relative component relative compact if C closure be compact. Okay, now write this example here. Let x equal to r and c equal to 0 1, and then c closure equal to position a compact set okay, then then C01 be relatively compact. Okay, now we erase our portion and we also going to another example of relative compact. Okay, now let x dx y dy be matrix spaces and let cxy be the set of all continuous mapping from x into y from x into y and kxy equal to set of all linear compact linear compact operators. Okay, then cxy be the set of all continuous mapping from x to y and kxy be the set of all linear compact operators. Okay, next we define here let xy be norm spaces. Let xy be norm spaces and bxy be norm space. Bxy be norm space. Then norm of t difference x equal to supremum of x belongs to x is not equal to 0. Norm of t difference is x divided by norm of x equal to, so kxy subset of bxy. Now we also discuss here for st sub belongs to kxy and alpha belongs to K, then S plus T x equal to Sx Tx, and alpha is x equal to alpha is x. Okay, now we also discuss another proposition. Now we see about that another proposition. We erase this portion and then going to another proposition. Let x and y be normed spaces. X and y be normed spaces. Then kxy, then kxy be a subspace of bxy. Let st belongs to kxy and alpha belongs to k. We have to show that s plus alpha t belongs to kxy. For this let xn be a sequence in x. Xn be a sequence in x. Since S and T are compact, then we have found. Then we can find. Then we can find the subsequence x and k is subsequence x and k of xn such that this x and k and p and p x and k are convergent. So thus s plus alpha t x n as a convergent subsequence. Okay, as a convergent subsequence s plus alpha t x. Next we discuss about closeness of cxy. That means kxy be have a subsequence of pxy, then kxy is a subsequence subspace of b, sorry, kxy is a subspace, then that means x plus alpha t belongs has a subsequence, has a convergent subsequence. Okay, now we also erase this portion and discuss about that. Here kxy subspace of bxy. Now closedness of cxy and obviously kxy. Okay, closedness tn in cxy with tn tends to t belongs to bxy. This implies t belongs to cxy and c is closed in xt, and if xn in c, if xn in c with xn converts to x belongs to this x, this implies x belongs to c. Okay, this implies x belongs to c. Next we discuss also some theorem. Here x norms is and y Banach space. Then kxy closed subspace of dxy. Okay, even x belongs to kxy and t belongs to kyz. This implies t is belongs to kx. Okay, then again we discuss about equicontinuous. Okay, equicontinuous we discuss now here, and obviously uniformly equicontinuous. We now discuss here, and then we going to another theorem. Okay, so we erase this portion and going to now definition of equicontinuous. Here we write let this a subset of cxy, then a is called, then this a is called equicontinuous at a point, equicontinuous at a point x belongs to x if for each epsilon greater than j, if for each epsilon greater than 0, there exists delta equal to delta epsilon x greater than 0, such that dy fx fy less than epsilon for all xy belongs to x, with dx xy less than delta for all f belongs to this delta. A subset of C x to y. A is called equicontinuous at a point x belongs to x. If for each epsilon greater than 0, there exists delta epsilon x greater than 0, such that distance in respect to y, fx and fy, distance of fx and fy in respect to y less than epsilon for all xy belongs to x, with distance of xy with respect to x less than delta, and for all a belongs to a. Then this collection is called equicontinuous. Now uniformly equicontinuous. Uniformly equicontinuous. Okay, we write just definition of that. Here, here obviously let this script a subset of cxy, and then this script a is called uniformly equicontinuous. Equicontinuous if for each epsilon, if for each epsilon greater than 0, there exists delta epsilon greater than 0, such that dy fx fy less than epsilon for all xy belongs to x, satisfying d of x xy less than delta for all a belongs to the script. Okay, then this collection of continuous operator from x to y is called equicontinuous if for epsilon greater than 0, there exists delta epsilon greater than 0, such that dy of fx and fy, that means distance of fx fy with respect to y less than epsilon for all xy belongs to x, satisfying distance of xy with respect to x less than delta for all f belongs to this 50 collection a. And then here delta obviously depend on epsilon, and in equicontinuous here delta obviously will depend on epsilon and x. So today we stop here.